Okay, let's get started. So, the purpose of today is to do a little bit of forward thinking and design before I actually build the neural network. So, I call this a design sprint. I don't know, hopefully it'll actually be a sprint. We'll see how long this video takes. This isn't, I'm not going to, I'm going to give a little bit of background into neural networks, but not gratuitously. If you find yourself not fully comprehending the concepts, you might want to watch. There are several videos on YouTube. I really recommend the one by 3 Blue, 1 Brown. That one is pretty good. He explains it very well, and it's really, really thorough. He has like a series of 4 videos, each going into deeper and deeper depth, and it's really well explained. But if you understand the basics, this should make sense. And even this might be too much, depending on how much you already know. So in any case, I want to create a neural network where the final output neuron corresponds to whether or not the computer will hit this, well, it will not hit the space bar, but whether or not it will go up or allow itself to fall down. When the human is playing, this corresponds to hitting the space bar or not. That determines whether you accelerate up or you accelerate down by gravity. So I have some set of input neurons, and then I have another hidden layer of neurons, and each neuron in a given layer is connected to every other neuron in the following layer, and that's what these lines represent. These are called weights. They're weights between the neurons. They're denoted in blue, and then the neurons or activations are denoted in red, and these biases are denoted in green. So each neuron in one layer depends on every single neuron in the previous layer, with weights, and then you also have biases. Here I'm denoting the layers, so I have 3 layers here. I have layer 1, layer 2, layer 3, input, hidden, output. Here's a little bit of notation before I get into some equations. So each neuron has a value, also called like an activation, and I use the subscript ij to denote the activation of neuron j in layer I. So here in this layer, I equals 2, this is I equals 1, I equals 3. This is j equals 2. So this is, the value of this neuron is A12. The value of A12 is the value of this neuron. B sub I is just the bias of layer I. So the value of this bias here is equal to B sub 2. This is B sub 3. And then the weights, I use 3 subscripts. I'm not sure how common this is, but it makes it easier for me to take note of things. So Wij is the weight for neuron K in layer I plus 1 with respect to neuron J in layer I. So for example, this neuron, this is the first neuron in the second layer. This is the first neuron in the first layer. So the weight between them would be denoted W1, 1, 1. That's the simplest one, W111, because it's connecting layer 1 in, neuron 1 in layer 2 with neuron 1 in layer 1. This one here connected to this one would be weight W112. Get it? 112. And then in this case, it would be W for this one connecting to this one. It would be W 1, 2, 1. Because it's layer 1, neuron 2 connecting to neuron 1 in layer 2. It's kind of convoluted, but the indices help, and this will help with the coding later, because so each set of weights between any 2 layers can be represented as like a matrix. So there's like a 5 by 2 matrix that would represent the weights of all of these numbers, of all the weights between all these neurons. This one, it would be a 2 by 1 matrix. That's pretty simple. And then I also have the biases. So these are the tunable parameters, the weights and the biases, and these are the things you're trying to optimize when you run this problem. You're trying to improve the score by optimizing the dependence of the output on the inputs as fed through the neural network. So how do the weights and the activations interact? So the input neurons actually don't have an activation. They're just values that are fed in directly from the program. But how are these activations determined? So they interact with the weights and the activations on the previous neurons in a specific way. And the way it starts is it as a linear combination. So like, let's say we're looking at this neuron. This is the first neuron in the second layer. So in this case, I is equal to 1, so z sub 2, and k is equal to 1. So it's so you start with, you add the bias to the weights times the activations of all of the neurons in the previous layer. So that's how that works. So it's just a linear combination of all of these activations in the previous layer, where the linear coefficients are the w, I, j, k, the weights, basically. So that's how they interact. That's how this gets created, and then that's how this one gets created. So in this layer, it's a linear combination of these two, and it has its own weights. The idea is to optimize the weights and the biases such that to maximize the survival time in my case. So once you do this linear combination, that's actually not the activation. You still need to do another operation. So you get this, what I'm calling z, I plus 1 comma k. So it's z in layer I plus 1 and the kth neuron. So I plus 1th layer and the kth neuron has a z value based on this linear combination. From there, you take this z thing. So this is the equation from the previous slide. And then the activation on this neuron is actually a function of this z value. You always use a nonlinear function. In my case, I'm going to use a sigmoid function, which varies between 0 and 1 with an input from negative infinity to infinity of x. So phi of x has this form, 1 over 1 plus e to the minus x, and it looks like this. And yeah, so that's how you do that. And it's centered about the bias. So this is good. This gives me something to where, like, say I have a value greater than a half, then the computer tells the ship to go up, and if it's less than a half, then it lets it fall down. So the way this neuron depends on all of the inputs can be optimized by optimizing the weights and the biases. So that's exactly what happens here. I hope I'm being clear. Yeah. So in every forward neuron, you have a dependence on the previous neurons based on the weights and the bias, and then you go to the next neuron, and then until finally you're at the output layer, and then you basically optimize those things to improve your metric. In some cases, the metric is strictly the value of this thing, and in which case you can do an error function, and then you can optimize your weights and biases to minimize your error, i.e. the difference between the output neurons and what they're actually supposed to be. This is the way like these image things work, where they like those image processing algorithms where they can look at handwriting and stuff. There's actually a right answer. But in my case, there's no right answer for this output neuron. It's just saying hit spacebar, don't hit spacebar, depending on the inputs, which would be like maybe the positions of the player and the lasers or what have you. So what I actually have to do is I have to do a genetic algorithm where I create a bunch of different variations of weights and biases, random variations, and I just run them all and I allow the best ones to breed. So that takes me to the next slide. So I initialize, so like let's say these are my inputs, like this is the case where I would only have one laser. I would initialize my weights and my biases randomly for every single variation. Maybe I'd have hundreds of variations. And then I would just let the games play out and see how long each of these iterations survived. And like I said, the output neuron is between 0 and 1, and less than half could be no, and greater than half could be yes. And then I would iteratively select for the best networks, basically the ones that survived the longest in the game. And I would allow for breeding and mutation to improve the network as generations progress. The way I decide to breed these parameter sets, I'm not familiar with the common algorithms, but I presume like you just have maybe a child is like the average of the two parents, or somewhere in that ballpark, and then you have a probability of mutation, and that's how these things work. But I'm not actually familiar with this. But I think I'm just going to give it a go. I'm not going to do any reading, and I think it'll end well. So yeah, this is how I plan to approach this problem. And one last thing before we proceed with the implementation of the neural net, I want to get into some basic matrix multiplication and verify that we know exactly what's going on, and I want to try to briefly explain the significance of matrix multiplication and how it simplifies the coding of the training of the neural net. So, say we have two matrices, A and B, and we want to multiply them. A times B. A is 1, 3, 5, 7. Oh, whoops. That's not correct. B is supposed to be 2, 4, 6, 8. So B is 2, 4, 6, 8. Just imagine that this is this. So B is 2, 4, 6, 8. This is a typo. And what I typically do when I am doing a matrix multiplication is I write it like this. So I have A over here and B over here. I put A at the bottom left, and like imagine this is a quadrant, and B at the top right, and these two are being multiplied. And the reason I do that is because the way you get like this element of the product matrix is you multiply this row by this column. So you do 1 times 2 plus 3 times 6. So 2 plus 18 is 20. And then this element is 1 times 4 plus 3 times 8. This element here is this row times this column. 5 times 2 plus 7 times 6. This final element is 5 times 4 plus 8 times 7. And this can be represented symbolically like the following. Any general matrix A times matrix B is equal to this matrix. So you can prove it to yourself if you want by adding up all these values and computing these, that this is equal to this. This is always true. Likewise, you can multiply a 2 by 2 matrix A times a column vector C and get another column vector. And it can be shown that this relationship is also true. So anywho, so let's just see if we know what we're doing. Go ahead and close this for now. Save. So I've just rigged the code to do a matrix multiplication. So I have these two matrices, A and B, just like before. Oh, maybe I shouldn't have closed that. Whoops. Maybe I should not have closed that. Okay, So I didn't want to close that. It's back open. Let's just minimize it. So I have these two matrices, and I want to see if I get the same answer when I multiply them. So I want to do console.log math. So I'm using the math.js library, which I'll get a little bit more into in the next video, but that's a library we need to do this type of stuff. Math.multiply this.a, this.b. So I'm multiplying this matrix by this matrix, and I'm printing that. So if I go to the console, 20, 28, 52, 76. 20, 28, 52, 76. Okay, so here in the code, you have open bracket, row 1, close bracket, comma, open bracket, row 2, close bracket, close bracket. So that's what you do. Basically it's row major. So you do the rows. You order the rows and not the columns. So that's the important thing. Make sure I wanted to make sure it was row major and not column major because it varies between programming languages. And if I had these rows and columns flipped, and I had instead of 1, 3, 5, 7, I had 1, 5, 3, 7, and instead of 2, 4, 6, 8, I had 2, 6, 4, 8. The answer would be completely different, and so it would be wrong actually. So that's the important thing, is to make sure that we have this all sorted out correctly. One other thing that I should maybe point out. So how does this exactly connect to the neural net? Might as well get specific here. So here's the original graphic. You remember this notation. You have to do some linear combination of the values of the activations in the previous layer using the weights to get these z values, and then you apply the activation function to the z values. So getting these z values can be expressed as a matrix multiplication. So this index I is just indicating where we are along this progression. So like if we're looking at the connection between layer 1 and layer 2, then I'm saying index I is equal to 1. So in any given forward propagation from one layer to another, we have a single index I. And then we have additional indices j and k, which indicate which layer we're working with on which neuron. So if we look at this here, we have this W matrix, the weights matrix, times the activations matrix. So this is the activations on the layers in this neuron if we're looking at layer 1. And then all of these weights form a matrix. You multiply these matrices to get this what I call zi plus 1 matrix. So each of these values in this matrix is equal to one of these equations. Also, we have to add the bias, which I haven't shown. W11 times A1 plus W12 times A12, or A2. So this index, this J index, is indicating the neuron number in layer I. The same with this J matrix, this J index. And then the K index is indicating the neuron number in the second layer, I plus 1. So W12 connects the first neuron in this layer with the second neuron in this layer. So each of these indices, each of these elements in this W matrix corresponds to a connection between a neuron in the previous layer with a neuron in the following layer. And that's, yeah. And these don't have to be square matrices, they can be rectangular matrices. As long as, like this could be a 2 by 5 matrix, which is what it would be here, and this would be a 2 by 1 matrix. Or no, this would be a 5 by 1 vector. So as long as they have the same dimension, a single dimension that's matching, that you can multiply them. Let's see. Yeah. So I don't know if this made this more clear, but yeah, that's how we do that. So for each set of neurons that are connected, we're going to have a W matrix. So if our neural net looks like this, we're going to have 2 W matrices and 2 A vectors. Well, 3 A vectors, but 2 that'll be used in this operation. And then finally, we get our final output. We get our activation on the output neuron, and that will be controlling the response of the player. That will be controlling how the player operates. And basically, we're going to be using a genetic algorithm to optimize these W values and to optimize these bias values, which will also go here, that are not shown. So yeah, so this will make the implementation much easier, because we just create 2 matrices. We create a bunch of matrices, and then we just apply a multiplication operator that gives us these. And then that'll give us these Z values. Then we apply the activation function. That'll give us the activations. Then we just do the matrix multiplication again. Then we get this Z value, and then we apply the activation, and boom. That will just give us our outputs. It'll be very fast and straightforward. And since we won't be dynamically training the neural networks during the gameplay, this propagation will only happen once for each player, for each time it plays. And then the game will just go, because the outputs will be set. So the game won't run any slower because of the neural network, is my point. And yeah, and then after all the players die, I'll simply I don't think I'll run the genetic algorithm right away. I think I'm gonna let each generation play a certain number of games until it's exposed to a certain number of spears, or lasers rather, because I want it to sample a representative distribution of spear velocities, because, like, if you recall, the spear velocity distribution is Gaussian. So they actually need to see enough spears for me to know, like, how good they actually are. Like, the survival time for one game probably isn't enough data for me to know how good the spears are. I'll probably have some kind of criterion that I set that decides whether or not I have enough information to know how good these players are before I apply the genetic algorithm. At that point, then I will apply the genetic algorithm to breed the most fit players, and I'll apply some mutation and some random mutations, and we'll see how it goes. I might need to do more research, but that's the plan so far. So anyway, I'll see you next week. We will be starting the implementation of this, and hopefully it'll go well. So have a good day. Goodbye. So I just realized that I misspoke when I said that the outputs on the outputs won't be being evaluated dynamically during the gameplay. That's actually false, because the outputs depend on the player position and velocity, and as well as the lasers, and these are changing dynamically throughout the gameplay. And obviously, whether or not it hits spacebar is a dynamic decision. So what's not changing are the weights and the biases throughout the gameplay, but the output actually will change. So I thought I would correct that and just say that. So yeah, this will be changing dynamically. So I don't know actually how this continuous because this propagation has to occur every single frame. I mean, well, I guess it doesn't have. I don't know. I guess I could change the frequency of propagation depending on and see if that matters. But the point being is it's going to be continuously doing this propagation for every single player that's alive. And that may slow down the performance. I don't know. I can always change the number of players. I can change, like I was just saying, the propagation frequency. We'll see how it works out, but this very well may affect the performance. Okay.